The ocean plays a role in your life long before you ever see it. Every second you breathe, a large portion of that oxygen is coming from the sea. Tiny drifting organisms, especially microscopic algae known as phytoplankton, quietly produce more than half of the oxygen in the atmosphere. They are invisible to the naked eye, yet they work on a scale so massive that they help sustain nearly all life on Earth. It's easy to think of forests as the lungs of the planet, but in reality, the ocean is just as important, if not more. And yet, despite how much we depend on it, the ocean remains one of the least understood places on Earth. In fact, what we know about the ocean is surprisingly small compared to what remains hidden. Scientists estimate that around 80% of the ocean has never been fully mapped, observed, or even seen by humans. Vast regions lie in complete darkness, untouched and unexplored, as if they belong to another world entirely. There are mountains, valleys, and entire ecosystems down there that no human has ever witnessed. For all our technology and exploration on land and even in space, most of the ocean still remains a mystery. And when you begin to look deeper into it, that mystery quickly becomes something much more extreme. Far below the surface lies the deepest known point in the ocean, a place called Challenger Deep, located within the Mariana Trench. It reaches a depth of nearly 11 kilometers, which means if Mount Everest were placed inside it, the peak would still sit more than a mile underwater. At that depth, sunlight cannot reach, and the environment becomes completely dark and silent. The distance alone is difficult to imagine, but what truly defines this place is not just how deep it is, but the conditions that exist there. As you descend toward the bottom of the Mariana Trench, the pressure begins to rise rapidly. By the time you reach Challenger Deep, the pressure is more than 1,000 times greater than what you experience at sea level. It is so intense that it can crush most submarines and would instantly destroy any unprotected human body. Every square inch of space is being pushed by an enormous weight of water from above. And yet, even in this crushing environment, life still manages to exist, adapting in ways that seem almost impossible, even in places where the ocean seems empty and undisturbed. It is quietly holding onto pieces of human history. Scattered across the seafloor are the remains of ships, cargo, and entire journeys that never reached their destination. Over centuries, countless vessels have been lost to storms, navigation errors, or conflict, each one carrying objects from its time. When all of these are added together, the ocean floor holds more historical artifacts than all of the world's museums combined. Unlike museums, where items are carefully preserved and displayed, these artifacts lie exactly where they were lost, slowly being reclaimed by the sea. Wood breaks down, metal corrodes, and marine life begins to grow over everything, turning wrecks into artificial reefs. Some sites remain frozen in time, still containing personal belongings, tools, and cargo that tell silent stories about the past. Others have been discovered by explorers, offering rare glimpses into history, but the vast majority remain untouched, hidden in deep and inaccessible waters. It is a kind of archive unlike anything on land, one that continues to grow with every passing year. And while these lost objects rest quietly below, the ocean is also holding something far more surprising, something far more valuable than anything stored in a museum. Dissolved within seawater is an enormous amount of gold, spread so thinly that it is almost impossible to notice. Scientists estimate that the ocean contains around 20 million tons of gold, making it the largest reservoir of the metal on Earth. Unlike gold found in rocks or riverbeds, this gold does not exist in visible pieces or nuggets. Instead, it is broken down into microscopic particles and evenly distributed throughout the water. In a single liter of seawater, the amount of gold is so small that extracting it would cost far more than the gold itself is worth. This is why, despite its vast quantity, ocean gold has never been successfully mined on a large scale. The idea of pulling gold from the sea has fascinated people for generations, but the reality is far less practical than it sounds. It remains out of reach, not because it is scarce, but because it is too dispersed to collect efficiently. Still, the fact that such an immense amount of wealth exists all around us, invisible and untouchable, adds another layer to how unusual the ocean truly is. And hidden within that same water are even more unexpected elements. Among the many substances dissolved in seawater, there are also trace amounts of radioactive elements, including uranium. This means that, in a very slight and natural way, seawater is mildly radioactive. However, the levels are extremely low, so low that they pose no harm to humans or marine life. The uranium present in the ocean comes from rocks on land, where it slowly breaks down and is carried into the sea by rivers over long periods of time. Once there, it becomes diluted across the vast volume of water, reducing its intensity to safe levels. In fact, the amount of radiation you would be exposed to while swimming in the ocean is far less than what you experience from natural sources on land, such as the soil beneath your feet or even the air around you. It is simply another example of how the ocean contains a complex mixture of elements, many of which we rarely think about. Beneath its surface, it is not just water, but a constantly shifting chemical system, holding everything from valuable metals to trace radioactive particles, all balanced in a way that allows life to continue undisturbed. If you could isolate a single cubic mile of seawater and examine everything dissolved within it, you would find that it contains a surprising amount of gold. On average, that volume of water holds about 25 pounds of gold, spread out in an incredibly diluted form. At first, that might sound like a large and valuable amount, but when you consider the sheer size of a cubic mile of water, the concentration becomes almost meaningless. The gold is broken down into tiny particles, invisible and evenly dispersed, making it nearly impossible to extract in any practical way. To collect even a small amount, you would need to process enormous volumes of seawater, using more energy and resources than the gold would ever be worth. This is why, despite the ocean holding vast quantities of precious metals overall, it remains an untapped source. The gold is there, but it is locked within the water itself, too thinly spread to be gathered. It exists more as a scientific curiosity than a usable resource, a reminder that the ocean contains far more than what we can see or easily access. And while some of these hidden elements remain silent and invisible, the ocean itself is never truly quiet. Even when the surface appears calm, the ocean is constantly producing sound. Beneath the waves, there is a low, continuous vibration known as the Earth's hum. This is not a sound you can hear with your ears, but it can be detected using sensitive instruments like seismographs. The hum is created by the interaction between ocean waves and the sea floor, as well as the movement of water across vast distances. As waves travel across the ocean, they generate pressure that reaches deep below, causing the Earth itself to vibrate slightly. These vibrations form a steady, background signal that can be measured around the world. It is always present, whether or not there are storms or strong winds, forming a kind of natural rhythm that never fully stops. Scientists study this hum to better understand both the ocean and the structure of the planet beneath it. It reveals that even in moments of stillness, there is constant motion happening on a scale far beyond what we can sense directly. And within this moving, vibrating environment, sound behaves in a very different way than it does in the air above. In water, sound travels much faster and farther than it does through air. On average, it moves about 4.3 times faster, allowing it to cover enormous distances with very little loss of energy. This is why sounds in the ocean can travel for thousands of kilometers, especially in deep water where conditions are stable. Marine animals have adapted to this property in remarkable ways. Whales, for example, use low-frequency calls that can move across entire ocean basins, allowing them to communicate with others far beyond the range of sight. A single call can travel so far that it may be heard by another whale days later, on the other side of the ocean. This ability to send and receive sound over long distances is essential in an environment where visibility is often limited. It turns the ocean into a place where sound becomes the primary way of sensing the world. What might seem like silence from above is, in reality, filled with echoes, signals, and distant calls moving continuously through the water. Deep within the ocean, there is a unique layer of water that behaves in a way that almost feels engineered, even though it is entirely natural. This layer is known as the SOFAR channel, short for sound fixing and ranging channel, and it acts like a kind of underwater sound highway. It forms at a specific depth, where water temperature and pressure combine in such a way that sound waves become trapped instead of spreading out in all directions. Normally, sound energy fades as it moves, but inside this channel, it can travel with very little loss, guided horizontally across vast distances. Because of this, a sound made in one part of the ocean can move thousands of kilometers and still remain detectable. Marine animals, especially whales, take advantage of this phenomenon. Their low-frequency calls can enter this channel and travel across entire ocean basins, allowing communication over distances that would otherwise be impossible. It turns the ocean into a connected acoustic network, where messages can move far beyond what the eye can see. Scientists have also used the SOFAR channel for tracking and studying underwater activity, further proving how powerful this natural system is. This mysterious signal became known as the bloop. What made it so unusual was not just its volume, but its scale. The sound traveled across an estimated 5,000 kilometers, suggesting a source of immense energy. At the time, its origin was completely unknown, leading to speculation ranging from undiscovered marine life to unusual geological activity. The idea that something large enough to produce such a sound could exist in the deep ocean captured the imagination of many. Over time, scientists leaned toward a more natural explanation, suggesting that the bloop was likely caused by an ice quake, where large masses of ice crack and shift, releasing powerful acoustic energy into the water. Even so, the event remains one of the most famous unexplained ocean sounds ever recorded, a reminder of how much of the ocean's behavior we are still trying to understand. And while some ocean phenomena seem mysterious because of sound, others appear unusual simply because of how they look. Near the island of Mauritius in the Indian Ocean, there is a place where the sea appears to behave in a way that seems impossible at first glance. From above, it looks as though a massive underwater waterfall is pouring off the edge of the ocean floor, as if water is cascading into a deep abyss. The effect is so convincing that it has captured global attention, often described as one of the most stunning natural sights on Earth. However, this is not a real waterfall. What creates this illusion is the movement of sand and sediment along the edge of a continental shelf. As ocean currents push these particles downward, they form patterns that resemble flowing water, creating the appearance of a waterfall beneath the surface. The clarity of the surrounding water and the contrast in color make the effect even more dramatic when viewed from above, especially from aircraft or satellites. It is a powerful example of how the ocean can create visuals that challenge our expectations, turning simple natural processes into something that feels almost unreal. Deep on the ocean floor, in places where sunlight never reaches, there are formations that look almost impossible at first glance. These are underwater rivers and lakes, created by extremely salty water known as brine. This water is far denser than the surrounding seawater, which causes it to sink and settle along the seafloor instead of mixing. Over time, it forms distinct pools that behave in ways very similar to bodies of water on land. They have clear boundaries that resemble shorelines, and in some cases, small wave-like movements can be seen along their edges. When remotely operated vehicles explore these areas, the visual contrast is striking. The brine often appears darker and more opaque, separating itself from the clearer water above it. It can even flow slowly across the seafloor, creating the appearance of an underwater river cutting through the deep ocean landscape. These environments are not just unusual in appearance, they also host unique chemical conditions that support specialized forms of life. Certain microorganisms have adapted to survive within or around these pools, feeding on the chemicals present in the dense water. It is a reminder that even in the most extreme and unfamiliar parts of the ocean, life finds a way to exist. But for most creatures, these environments are far from safe. The same properties that create these brine pools also make them extremely dangerous to typical marine life. Because the water is so heavily saturated with salt and other dissolved substances, it becomes toxic to many organisms. Fish that accidentally swim into these pools often cannot survive. The sudden change in salinity disrupts their biological systems, making it difficult or impossible for them to function. In some cases, animals become disoriented at the boundary, struggling to escape once they cross into the denser layer. Over time, the remains of these creatures can accumulate along the edges of the pool, creating a stark and unsettling scene on the ocean floor. It is almost like a natural trap, where the conditions themselves act as a barrier between survival and death. Despite this, certain specialized organisms continue to thrive in these extreme conditions, feeding on the chemical-rich environment that would be lethal to others. These pools highlight how drastically different the ocean can be, even within relatively small areas. And while these deadly environments exist quietly on the seafloor, there are much larger and more dynamic forces constantly moving through the deep ocean. Far beneath the surface, the ocean is not still or silent. It has its own complex weather system, operating entirely out of sight. Deep underwater, there are powerful currents that behave like storms, moving vast amounts of water across the ocean floor. These currents can form swirling whirlpools and internal waves that travel through layers of water with different densities. Some of these waves can reach heights of hundreds of meters, far larger than most waves seen on the surface. Yet they remain hidden, moving slowly through the depths without ever breaking above. These internal waves are often created by differences in temperature and salinity, which cause layers of water to shift and interact. As they move, they can influence the distribution of nutrients, shape underwater landscapes, and even affect marine life. To us, the ocean's surface may appear calm, but below it, there is constant motion, driven by forces that are just as powerful as weather systems in the sky. It is a hidden world of movement, where storms exist without wind, and waves travel in complete darkness. Far below the surface, where sunlight cannot reach and the ocean appears completely still, there are waves moving silently through the depths. These are known as internal waves, and unlike the waves we see breaking along coastlines, they travel between layers of water with different densities. What makes them remarkable is their scale. Some internal waves can grow to heights greater than the Empire State Building, rising hundreds of meters from trough to crest. Yet, despite their immense size, they remain completely hidden beneath the surface, moving slowly through the ocean without any visible disturbance above. These waves form when currents push against underwater features like ridges or continental slopes, causing layers of water to shift and rise. As they travel, they can carry energy across long distances, mixing nutrients and influencing marine ecosystems along the way. For deep-sea organisms, these waves are a constant force, shaping their environment in ways that are difficult to imagine from above. It is a reminder that the ocean is not a static place, but a dynamic system where massive movements can occur in total darkness. And in that same dark environment, there are places where the ocean behaves in ways that seem even more extreme. On the ocean floor, in regions where the Earth's crust is thin or active, there are openings known as hydrothermal vents. These vents release superheated water from beneath the seafloor, sometimes reaching temperatures of over 400 degrees Celsius. Under normal conditions, water at that temperature would boil instantly, but at these depths, the pressure is so intense that boiling cannot occur. Instead, the water remains in a liquid state, carrying dissolved minerals as it bursts out into the surrounding ocean. As the hot fluid meets the colder seawater, minerals begin to solidify, forming towering structures that resemble chimneys. These formations continue to grow over time, creating entire fields of vents across the seafloor. The environment around them is harsh, dark, and chemically rich, unlike anything found at the surface. Temperatures can shift rapidly within short distances, and the water is filled with substances that would be toxic in most other settings. Yet, despite these extreme conditions, these areas are far from lifeless. In fact, they would soon reveal something that would change how we understand life itself. In 1977, scientists exploring the deep ocean made a discovery that challenged long-held beliefs about where life could exist. Around hydrothermal vents, they found thriving communities of organisms living in complete darkness, far from any source of sunlight. Until that point, it was widely assumed that life on Earth ultimately depended on energy from the sun. But these ecosystems operated differently. Instead of photosynthesis, where organisms use sunlight to produce energy, these deep-sea communities relied on a process called chemosynthesis. Microorganisms used chemicals released from the vents, such as hydrogen sulfide, to generate energy, forming the base of an entirely separate food chain. Larger organisms, including tube worms, clams, and other specialized species, depended on these microorganisms to survive. It was a discovery that reshaped our understanding of biology, proving that life could exist in environments once thought to be completely uninhabitable. It also opened new possibilities for where life might be found beyond Earth, suggesting that even in dark and extreme conditions, life can find a way to emerge and endure. Around hydrothermal vents, where superheated water bursts from the seafloor and sunlight never reaches, some of the most unusual organisms on Earth can be found. Among them are giant tube worms, creatures that can grow up to 2.4 meters in length and live for more than 200 years. They have no eyes, no mouth, and no digestive system in the way most animals do. Instead, they rely entirely on a relationship with microscopic bacteria that live inside their bodies. These bacteria use chemicals from the vent fluids to produce energy through chemosynthesis, effectively feeding the tube worm from within. The worm provides the bacteria with access to hydrogen, sulfide, and oxygen, while the bacteria supply the nutrients needed for survival. It is a perfectly balanced partnership that allows both to thrive in an environment that would otherwise be uninhabitable. The red plume at the top of the tube worm helps absorb these chemicals from the surrounding water, giving it a distinctive appearance against the dark seafloor. Despite the harsh conditions, these organisms grow slowly and can live for centuries, making them some of the longest living animals in such extreme environments. Their existence shows how life can adapt in ways that seem completely unfamiliar, finding stability even in places shaped by heat, pressure, and darkness. And yet, even more unusual forms of life exist in the deep ocean, feeding not on chemicals from the earth, but on the remains of some of the largest animals to ever live. First, when a whale dies and its body sinks to the ocean floor, it does not simply disappear. Instead, it becomes the center of a complex and long-lasting ecological process known as a whale fall. One of the most unusual creatures associated with this process is the zombie worm, scientifically known as Osedax. These worms have no mouth and no stomach, yet they are able to feed by breaking down the bones of the dead whale. They do this using root-like structures that extend into the bone, secreting acids that dissolve it and release nutrients. Inside these roots live bacteria that help process the material, allowing the worm to absorb what it needs to survive. From the outside, the worms appear as small, delicate structures rising from the bones, but beneath the surface, they are actively breaking down one of the densest parts of the whale's body. This process can continue for years, slowly recycling the nutrients locked within the skeleton. It is a highly specialized way of life, one that depends entirely on the presence of whale remains in the deep ocean. These organisms are part of a larger system that transforms death into a source of life, supporting an entire community over time. And what begins with a single fallen whale can eventually sustain a wide range of species in the depths below. A whale fall is not just a single event, but the beginning of an ecosystem that can last for decades. When a whale's body reaches the seafloor, it becomes a sudden and massive source of food in an environment where resources are often scarce. At first, larger scavengers such as sharks and deep-sea fish arrive to feed on the soft tissue, a process that can take months or even years. Once most of the flesh is gone, smaller organisms begin to take over, including worms, crustaceans, and bacteria that continue breaking down what remains. Over time, even the bones become a habitat, supporting species that specialize in extracting nutrients from them. This process creates a layered ecosystem where different organisms arrive at different stages, each playing a role in recycling the whale's remains. Hundreds of species can depend on a single whale fall, many of them found nowhere else. It turns an isolated event into a long-term source of life, sustaining organisms for decades in the deep ocean. In a place where food is limited and conditions are extreme, the fall of a single whale can reshape the surrounding environment, proving once again that even in the depths, life is constantly finding ways to continue. As you move down from the sunlit surface of the ocean, there is a region where light begins to fade, but does not disappear completely. This layer, known as the twilight zone, stretches from about 200 to 1,000 meters deep. It is a place of dim blue light, where visibility is limited and the environment begins to change rapidly. Despite the low light, this zone is far from empty. In fact, it contains more fish biomass than all the world's fisheries combined. Vast numbers of small fish, along with squid and other organisms, fill this layer in densities that are difficult to fully measure. Many of them participate in one of the largest daily movements on Earth, rising toward the surface at night to feed and descending again during the day to avoid predators. This constant vertical migration creates a hidden rhythm in the ocean, one that plays a major role in the global ecosystem. Yet, despite its abundance, this zone remains almost entirely unharvested. The depth, pressure, and difficulty of operating in such conditions have kept it largely untouched by large-scale fishing. It represents a massive, largely unexplored resource, but also a delicate system that scientists are still trying to understand. And as we look beyond the fish that fill these waters, there are structures in the ocean that are far larger and older than they first appear. When thinking about the largest living structures on Earth, many people immediately picture coral reefs, especially the Great Barrier Reef. However, deep beneath the ocean's surface, there are sponge reefs that rival and even exceed these well-known formations in scale. One of the most remarkable examples is formed by a deep-sea sponge known as Afrocolistes. These sponges grow slowly over long periods of time, creating complex, reef-like structures that can stretch for hundreds of kilometers along the seafloor. Unlike coral reefs, which rely on sunlight and warm, shallow waters, these sponge reefs exist in cold, dark environments, far from the surface. Their skeletons are made of silica, forming delicate, glass-like frameworks that build upon each other over generations. Over time, they create habitats for a wide range of marine life, offering shelter and stability in otherwise barren regions of the ocean floor. These reefs were once thought to be extinct, known only from fossils, until living examples were discovered in modern oceans. Their existence highlights how much of the ocean's large-scale structures remain hidden from view, quietly growing in places we rarely explore. And while some life forms build massive structures over centuries, others survive by constantly changing their own form. Among the many unusual creatures in the ocean, one of the most intriguing is the immortal jellyfish, known scientifically as Turritopsis dohrnii. Unlike most living organisms, which follow a one-way path from birth to maturity and eventually death, this jellyfish has the ability to reverse its life cycle under certain conditions. When it experiences stress, injury, or unfavorable environmental changes, it can transform its cells and return to an earlier stage of life known as the polyp stage. From there, it can grow again into an adult jellyfish, effectively resetting its biological clock. This process, called transdifferentiation, allows the organism to avoid death in a way that no other animal can. In theory, As long as it can successfully repeat this cycle and avoid being eaten or destroyed, it could live indefinitely. While it is still vulnerable to predators and disease, its ability to revert and begin again makes it one of the most unique life forms on the planet. It challenges the idea that aging is a fixed process, showing that in the ocean, even the basic rules of life can be bent in unexpected ways. Among the many forms of life in the ocean, jellyfish stand out as some of the simplest yet most enduring organisms ever to exist. They have no brain, no heart, and no blood, and their bodies are made up mostly of water. Instead of a centralized brain, they rely on a simple network of nerves that allows them to sense light, movement, and changes in their environment. They move by pulsing their bell-shaped bodies, drifting with currents while maintaining a surprising level of control. Despite this simplicity, jellyfish have survived for more than 500 million years, making them older than dinosaurs and even many of the earliest complex animals. Over time, they have adapted to a wide range of ocean environments, from shallow coastal waters to the deep sea. Their design has remained largely unchanged because it works, requiring very little energy while allowing them to feed, reproduce, and survive efficiently. Some species can deliver powerful stings, while others remain harmless, but all share the same basic structure that has persisted through countless changes in the planet's history. Their continued existence shows that complexity is not always necessary for survival, and that even the simplest life forms can endure across vast stretches of time. And while jellyfish represent simplicity, there are other creatures in the ocean that are just as ancient, but far more unusual in how they are classified. Deep in the ocean lives a creature known as the vampire squid, a name that suggests something familiar, yet it is neither a true squid nor an octopus. Instead, it belongs to its own distinct group called Vampiromorpha, a lineage that has remained largely unchanged for around 300 million years. This makes it a kind of living fossil, preserving characteristics from ancient ancestors that once inhabited the oceans long before modern marine life evolved. The vampire squid has a dark, almost black body, with webbing that connects its arms, giving it an appearance that is both delicate and unusual. It lives in deep, oxygen-poor environments where few other animals can survive, relying on specialized adaptations to endure these conditions. Rather than actively hunting prey like many cephalopods, it feeds on drifting organic material, conserving energy in a place where resources are limited. It can also produce bioluminescent light, using it as a defense mechanism to confuse potential predators in the darkness. Its unique classification highlights how diverse ocean life can be, with entire branches of evolution existing outside the categories we might expect. And while some deep-sea creatures remain small and hidden, others grow to sizes that are almost difficult to imagine. In contrast to the strange and shadowy life of the deep ocean, there are fish near the surface that reach extraordinary sizes, such as the ocean sunfish, also known as mola mola. This species holds the title of the heaviest bony fish in the world, with some individuals weighing as much as 2,300 kilograms. Its body is large, flat, and rounded, giving it a distinct shape that sets it apart from most other fish. Despite its massive size, it moves slowly through the water, often seen drifting near the surface or basking in the sun. What makes its life cycle particularly remarkable is the extreme difference between its early and adult stages. When it is born, a sunfish larva measures only about 2.5 millimeters in length, making it one of the smallest vertebrate larvae in the ocean. From this tiny beginning, it grows rapidly, increasing its size by millions of times over the course of its life. This dramatic transformation is one of the most extreme growth patterns found in any animal. It reflects the wide range of survival strategies that exist in the ocean, where life can begin almost invisibly small and develop into something enormous. Not all sharks live the same way, even though they may appear similar at first glance. Some species must keep swimming continuously in order to survive, because they rely on a process known as ram ventilation. As they move forward, water is forced through their mouths and over their gills, allowing them to extract oxygen. If they stop moving, that flow of water slows or stops entirely, and they risk suffocating. For these sharks, constant motion is not a choice but a necessity, shaping their behavior and migration patterns across the ocean. Species like the great white and certain types of reef sharks fall into this category, traveling long distances to maintain that steady flow of oxygen. At the same time, other sharks have developed a different method of breathing. They can actively pump water over their gills using muscles in their throat, allowing them to rest on the seafloor without losing access to oxygen. These sharks can remain still for extended periods, conserving energy and blending into their surroundings. This contrast shows how even closely related animals can evolve very different survival strategies depending on their environment. It is another example of how the ocean supports a wide range of adaptations, each suited to a specific way of life. And while sharks rely on movement or stillness to survive, other ocean creatures have developed abilities that seem far more extreme. Among the most remarkable animals in the ocean is the mantis shrimp, a small but incredibly powerful predator that defies expectations based on its size. Despite being only a few inches long, it can strike with a force comparable to that of a .22 caliber bullet. Its specialized front limbs act like spring-loaded clubs, accelerating with such speed that they can shatter the shells of crabs and other hard-bodied prey. The impact is so intense that it creates tiny shock waves in the water, adding even more force to the strike. But its physical power is only part of what makes it unique. The mantis shrimp also possesses one of the most advanced visual systems known in the animal kingdom. While humans have 3 types of color photoreceptors, allowing us to perceive a range of colors, the mantis shrimp has around 16. This gives it the ability to detect a much broader spectrum of light, including ultraviolet and polarized light. Its vision is not just about seeing more colors, but about interpreting the environment in ways that are difficult for us to fully understand. This combination of strength and perception makes it one of the most specialized predators in the ocean. And yet, Even this level of power is not the limit of what small marine creatures can do. Another tiny but extraordinary animal is the pistol shrimp, which uses a completely different method to defend itself and capture prey. Instead of relying on speed alone, it has one enlarged claw that can snap shut with incredible force. When the claw closes, it creates a rapid jet of water that forms a cavitation bubble. This bubble collapses almost instantly, producing a shock wave and a burst of energy strong enough to stun or kill nearby prey. What makes this phenomenon even more surprising is the temperature generated during the collapse of the bubble. For a brief moment, it can reach levels comparable to the surface of the sun, around 5,500 degrees Celsius. Although this temperature exists only for an instant and in a very small area, it demonstrates just how extreme physical processes can become in the ocean. The snapping sound is also loud enough to be detected over distances, adding to the shrimp's ability to interact with its environment. It is a striking example of how even the smallest creatures can harness powerful forces, turning simple movements into highly effective tools for survival. Octopuses are among the most unusual and intelligent animals in the ocean, possessing a biology that is very different from most other creatures. They have 3 hearts, with 2 dedicated to pumping blood to the gills and 1 responsible for circulating it to the rest of the body. Their blood is blue rather than red due to a copper-based molecule called hemocyanin, which is more efficient at transporting oxygen in cold, low-oxygen environments. But what truly sets them apart is their nervous system. A large portion of their neurons are not located in a central brain, but instead distributed throughout their arms. Each arm can sense, explore, and even make decisions independently to a certain degree. This means an octopus does not control its limbs in the same way humans do. Instead, its arms can taste and touch objects directly, reacting to stimuli without waiting for instructions from the brain. This allows the animal to perform multiple tasks at once, such as opening shells, exploring its surroundings, and avoiding predators simultaneously. Their flexibility, intelligence, and unique anatomy make them one of the most complex invertebrates in the ocean. It is a form of life that operates in a way that feels almost alien, showing how evolution in the ocean can take paths very different from those on land. And while octopuses rely on complex systems to survive, other ocean creatures have evolved solutions that are far more unusual in their simplicity. Among the many strange adaptations found in marine life, one of the most unexpected belongs to a type of sea cucumber. These soft-bodied animals, often found resting on the ocean floor, have developed a method of breathing that seems almost unbelievable at first. Instead of using gills or lungs in the way most animals do, certain species of sea cucumber breathe through their anus. Water is drawn in and expelled through this opening, passing over specialized internal structures that extract oxygen. This system allows them to remain mostly stationary while still maintaining a steady exchange of gases. It may seem unusual, but it is highly effective for an animal that spends much of its life on the seafloor, feeding on organic material in the sediment. In some cases, This same opening is also used for defense, as the sea cucumber can expel parts of its internal organs to distract predators before regenerating them later. These adaptations highlight how marine organisms can use parts of their bodies in ways that would seem impossible in other environments. It is another reminder that life in the ocean is shaped by conditions that demand flexibility and efficiency in unexpected forms. And as unusual as these adaptations may seem, there are creatures in the deep sea that take this concept even further by becoming nearly invisible. In the deep ocean, where light is scarce and visibility is limited, some fish have evolved bodies that are partially or completely transparent. This adaptation helps them avoid predators by making them difficult to detect in the dim environment. One of the most striking examples is the barrel-eye fish, a species with a transparent head that reveals its internal structure. Inside this clear dome are its eyes, which can rotate upward to look for prey silhouetted against the faint light from above. This unique feature allows the fish to scan its surroundings in a way that few other animals can. Its body remains mostly still as it drifts through the water, relying on its ability to remain hidden while observing what moves above it. Transparency in these fish reduces shadows and outlines, making them blend into the surrounding water. It is a highly effective strategy in an environment where being seen can mean the difference between life and death. These creatures demonstrate how evolution can produce solutions that seem almost unreal, allowing animals to adapt perfectly to the challenges of the deep ocean. In the deep ocean, where sunlight cannot reach, many animals rely on light that they produce themselves in order to survive. One of the most recognizable examples is the anglerfish, known for the glowing lure that extends from its head. At first glance, it appears as though the fish is generating this light on its own, but the reality is more complex. The glow is actually produced by symbiotic bacteria that live within a specialized structure at the end of the lure. These bacteria emit light through a chemical process, and in return, the anglerfish provides them with a stable environment and access to nutrients. This relationship allows the fish to create a steady, controlled source of light in complete darkness. The anglerfish uses this glow to attract prey, drawing smaller animals toward what appears to be a harmless flicker in the distance. When the prey comes close enough, the fish strikes quickly, capturing it before it can escape. This method is highly effective in an environment where food is scarce and encounters are rare. The ability to use living organisms as a source of light shows how deeply interconnected life can be in the ocean, with survival often depending on cooperation between entirely different forms of life. And in the case of the anglerfish, this unusual partnership is only part of an even more extreme way of living. Beyond its method of hunting, the anglerfish is also known for one of the most unusual reproductive strategies in the animal kingdom. In many species, the male anglerfish is significantly smaller than the female, sometimes reduced to a fraction of her size. In the vast and dark environment of the deep sea, finding a mate can be extremely difficult. So the male has evolved a solution that ensures he never has to search again. When he encounters a female, he attaches himself to her body by biting into her skin. Over time, his body begins to fuse with hers, connecting to her bloodstream and becoming permanently attached. As this process continues, the male loses many of his independent functions, including parts of his digestive system, relying entirely on the female for nutrients. In effect, he becomes a living extension of her body, existing solely to provide reproductive cells when needed. This adaptation ensures that reproduction can occur whenever the opportunity arises, without the need to locate another partner in the darkness. It is a strategy that may seem extreme, but in the deep ocean, where encounters are rare, it greatly increases the chances of survival for the species. And while the anglerfish relies on fusion for reproduction, other ocean creatures have developed equally surprising ways to defend themselves. In contrast to the strange biology of the anglerfish, the blanket octopus displays a different kind of adaptation, one based on both immunity and behavior. This species is known for its resistance to the venom of the Portuguese man-o'-war, a floating marine organism with tentacles that can deliver powerful stings. While most animals avoid these tentacles, the blanket octopus does the opposite. It actively seeks them out, tearing off sections of the tentacles and using them as tools for defense. By holding these venomous strands, the octopus effectively arms itself with a natural weapon, capable of deterring predators that would otherwise pose a threat. Its immunity allows it to handle the tentacles without harm, giving it a unique advantage in the open ocean. The blanket octopus also gets its name from the large, flowing membrane that extends between its arms, which it can spread out like a sheet when threatened. This makes it appear larger and more difficult to attack. Together, these adaptations create a combination of defense strategies that are both unusual and highly effective. It shows how some ocean creatures do not just avoid danger, but learn to use it to their advantage, turning potential threats into tools for survival. Among the many unusual adaptations found in the ocean, some sea slugs known as nudibranchs have developed an ability that blurs the line between animal and plant. After feeding on certain types of algae, these creatures do not simply digest everything they consume. Instead, they extract tiny structures called chloroplasts, which are responsible for photosynthesis in plants, and incorporate them into their own tissues. Once inside the slug's body, these chloroplasts can continue to function, allowing the animal to produce energy from sunlight in a process similar to plants. This ability is known as kleptoplasty, and it gives the nudibranch an additional source of energy beyond what it obtains from feeding. In environments where food may not always be available, this can provide a significant advantage. The slug can remain in sunlit areas, using light to sustain itself for extended periods. It is a rare example of an animal borrowing a biological function from another organism and making it part of its own survival strategy. This blending of roles challenges the usual distinction between plant and animal life, showing how flexible biological systems can be in the ocean. And while some marine creatures adapt by combining traits in unexpected ways, others take a different approach by moving between entirely different environments. At the edge where water meets land, There are fish that do something that seems almost contradictory to what we expect. The mudskipper is one such species, capable of leaving the water and moving across land for extended periods of time. It uses its pectoral fins like limbs, pushing and pulling its body forward in a motion that resembles walking or skipping. This allows it to navigate muddy shores, climb small surfaces, and even defend territories outside of the water. In addition to its movement, the mudskipper has developed a way to breathe air. It can absorb oxygen through its skin and the lining of its mouth, provided these surfaces remain moist. This means it must stay in damp environments to avoid drying out, but within those limits, it can function effectively outside the water. Its eyes are positioned high on its head, giving it a clear view of its surroundings both above and below the surface. This combination of traits allows the mudskipper to exist in a space between two worlds, taking advantage of resources that are not available to strictly aquatic or land-based animals. It is an example of how evolution can push the boundaries of what a fish can do. And sometimes, the ocean reveals creatures that do not just challenge expectations, but rewrite what we thought we knew about existence itself. For many years, the coelacanth was considered one of the most famous examples of an extinct species. Fossil records showed that this ancient fish had existed hundreds of millions of years ago, but it was believed to have disappeared around 65 million years ago, at the same time as the dinosaurs. Then, in 1938, everything changed. A living coelacanth was discovered off the coast of South Africa, astonishing scientists around the world. It was not just similar to the fossilized version, but almost identical in many ways, as though it had remained unchanged for millions of years. This discovery proved that some species can survive in isolation, hidden in parts of the ocean that are rarely explored. The coelacanth lives in deep waters, often near underwater caves and steep slopes, which likely contributed to it remaining undetected for so long. Its reappearance forced scientists to reconsider assumptions about extinction and survival, showing that the ocean can still hold species that we believe are long gone. It stands as a powerful reminder that there are still parts of the natural world that remain unknown, waiting to be discovered. In the cold, dark waters of the North Atlantic and Arctic Oceans, there lives a creature that challenges our understanding of lifespan. The Greenland shark is one of the slowest moving and least active predators in the ocean. Yet it may also be the longest-lived vertebrate on Earth. Scientists estimate that some individuals can live for up to 400 years, meaning a single shark could have been alive during events that occurred centuries ago. This extraordinary lifespan is linked to its environment and biology. Living in extremely cold water slows down its metabolism, reducing the rate at which its body ages. Growth is also incredibly slow, with some sharks taking over a century just to reach maturity. This means they live at a pace that is almost difficult to imagine, moving slowly through the depths while time passes differently compared to faster, more active animals. Their long lives also make them vulnerable, as populations recover very slowly if they are disturbed. The Greenland shark represents a form of life that is built for endurance rather than speed, surviving in one of the harshest environments on the planet. It shows that in the ocean, survival is not always about strength or aggression, but sometimes about patience and longevity. And while creatures like this move quietly through the depths, the ocean itself is constantly supporting life on a much larger scale. Although it is often overlooked, the ocean plays a critical role in maintaining the air we breathe. More than half of the world's oxygen is produced in the ocean, and most of it comes not from large plants, but from microscopic organisms known as phytoplankton. These tiny, drifting life forms float near the surface, where they receive enough sunlight to carry out photosynthesis. Using energy from the sun, they convert carbon dioxide and water into oxygen and organic matter, much like plants on land. Despite their small size, they exist in enormous numbers, covering vast areas of the ocean and producing oxygen on a global scale. Every second, they are contributing to the atmosphere, helping to sustain life across the entire planet. Without them, the balance of gases in the air would change dramatically, affecting ecosystems both on land and in the sea. It is easy to associate oxygen production with forests and vegetation, but in reality, the ocean is just as important, if not more so. This hidden process takes place continuously, largely unnoticed, yet it is essential for the survival of nearly all living things. And beyond producing oxygen, these same organisms also play a major role in regulating the Earth's climate. Phytoplankton do more than just produce oxygen. They are also responsible for removing a significant portion of carbon dioxide from the atmosphere, helping to regulate the planet's climate. Through photosynthesis, they absorb carbon dioxide and convert it into organic material, forming the base of the ocean's food chain. It is estimated that they remove roughly half of all carbon dioxide taken out of the atmosphere by natural processes. Some of this carbon remains in the upper ocean, supporting marine life, while some sinks deeper as organisms die or release waste, effectively storing carbon away from the atmosphere for long periods. This process is known as the biological carbon pump, and it plays a crucial role in controlling global carbon levels. Without it, carbon dioxide concentrations in the atmosphere would be much higher, leading to stronger warming effects. The activity of these microscopic organisms, therefore, has a direct impact on the entire planet, influencing both climate and life. It is another example of how the smallest forms of life in the ocean can have the largest effects, shaping conditions on a global scale in ways that are often invisible to us. Encircling the southernmost part of the planet is a body of water unlike any other. The Southern Ocean is the only ocean on Earth that has no true land boundaries separating it from others. Instead, it forms a continuous ring around Antarctica, connecting the Atlantic, Pacific, and Indian Oceans into one vast, uninterrupted system. What defines it is not the continents around it, but a powerful current known as the Antarctic Circumpolar Current, which flows endlessly from west to east. This current is the strongest on Earth, moving enormous volumes of water and playing a key role in regulating global climate. It helps isolate Antarctica by keeping warmer waters from reaching the continent, maintaining its icy conditions. At the same time, it connects the world's oceans, allowing water, heat, and nutrients to circulate on a global scale. The Southern Ocean is also one of the coldest and most extreme marine environments, yet it supports a range of life adapted to these conditions, from microscopic organisms to large marine mammals. Its open, boundary-free nature makes it unique among all oceans, acting as both a barrier and a bridge within the Earth's system. And as this ocean connects vast regions of water, it leads into an even larger body that dominates the planet, covering an area so vast that it is difficult to fully comprehend. The Pacific Ocean is the largest ocean on Earth, stretching across more space than all of the planet's land combined. It spans from the Arctic in the north to the Southern Ocean in the south, touching the coasts of Asia, Australia, and the Americas. Its size alone makes it a dominant feature of the planet, influencing weather patterns, ocean currents, and global climate systems. Within this immense expanse are countless islands, deep trenches, and underwater features, many of which remain unexplored. The Pacific also contains the deepest parts of the ocean, including the Mariana Trench, where conditions become more extreme with depth. Its vastness allows for a wide range of ecosystems, from warm, tropical waters filled with coral reefs to cold, nutrient-rich regions that support large marine populations. The scale of the Pacific means that events occurring in one part of it can influence distant regions, linking environments across thousands of kilometers. It is not just an ocean, but a system that shapes the planet on a global level. And beneath its surface, hidden from view, lies one of the longest geological features on Earth. Running through the world's oceans, largely unseen, is a massive underwater mountain chain known as the Mid-Ocean Ridge. Stretching for approximately 65,000 kilometers, it is the longest mountain range on the planet, far exceeding any range found on land. Unlike mountains formed by collisions between continents, this ridge is created by tectonic activity beneath the ocean floor. Here, Earth's plates are slowly moving apart, allowing molten material from below to rise and form new crust. As this material cools, it builds up over time, creating a continuous series of underwater peaks and valleys. Most of this ridge lies deep beneath the ocean surface, making it one of the least visible yet most important geological features on Earth. It plays a crucial role in the movement of tectonic plates and the renewal of the ocean floor. Along its length, hydrothermal vents and other unique environments can be found, supporting specialized forms of life. The mid-ocean ridge is a reminder that the ocean floor is not static, but constantly changing, shaped by forces deep within the Earth. Beneath the ocean's surface, far beyond what we can see or easily monitor, volcanic activity is constantly taking place. Submarine volcanoes erupt far more frequently than most people realize, with scientists estimating that they may erupt thousands of times each year. Unlike eruptions on land, these events usually go unnoticed because they occur deep underwater, hidden from direct observation. The ocean acts as a vast cover, absorbing the energy, heat, and material released during these eruptions. Lava flows out onto the sea floor, where it cools rapidly in the surrounding water, forming new rock and reshaping the landscape. In some cases, these eruptions can create entirely new underwater structures, gradually building up features over time. Occasionally, if the activity is strong enough and close to the surface, it can even lead to the formation of new islands. Despite their frequency, most submarine eruptions are only detected through indirect methods, such as seismic monitoring or changes in water chemistry. These hidden events play a major role in shaping the ocean floor, contributing to the continuous renewal of Earth's crust. They are a reminder that the planet is constantly active beneath the surface, even in places we rarely think about. And when you consider how often these eruptions occur, it becomes clear that the ocean is home to far more volcanic activity than we might expect. In fact, the majority of the planet's volcanoes are not found on land at all, but beneath the ocean. There are more volcanoes under the sea than on the continents, many of them located along tectonic boundaries, such as the mid-ocean ridge. These underwater volcanoes vary in size and activity, from small vents releasing heated fluids to massive structures capable of producing large eruptions. Because they are hidden beneath kilometers of water, they are far less studied than their counterparts on land. Yet they play an equally important role in Earth's geological processes. They help create new ocean crust, release gases from within the Earth, and influence the chemistry of the surrounding water. Some underwater volcanoes also support unique ecosystems, particularly around hydrothermal vents, where organisms thrive in conditions that would be hostile to most life. The sheer number of these volcanoes highlights how dynamic the ocean floor truly is, constantly shaped by forces from within the planet. It challenges the idea that the most dramatic geological events happen only on land, showing that much of Earth's activity is taking place out of sight. And as active as these volcanic systems are, they are only one part of a much larger and more complex underwater landscape. The ocean floor is far more varied than it might appear from above, containing features that closely resemble those found on land. There are mountains, valleys, rivers, and even formations that resemble lakes, all shaped by geological and chemical processes over time. One of the most remarkable examples of this complexity is found in the Denmark Strait, located between Greenland and Iceland. Here lies the largest waterfall on Earth by volume, and it exists entirely underwater. This massive flow occurs because of differences in temperature and density between two bodies of water. Cold, dense water from the Arctic sinks beneath warmer, less dense water, creating a downward flow that cascades over an underwater ridge. The drop is immense, far exceeding the height of any waterfall on land, and the volume of water moving through it is enormous. Yet, because it is hidden beneath the surface, it remains largely unknown outside of scientific study. This underwater waterfall is just one example of how the ocean contains landscapes as complex and dramatic as those on land, reminding us that much of the planet's most powerful features lie hidden beneath the waves. Deep beneath the surface of the North Atlantic, between Greenland and Iceland, lies one of the most powerful and least visible natural features on Earth. Known as the Denmark Strait Cataract, this underwater waterfall is the largest of its kind, dropping an astonishing 3.5 kilometers from top to bottom. To put that into perspective, it is far taller than any waterfall found on land. What drives this massive flow is the difference in temperature and density between cold Arctic water and warmer Atlantic water. The colder water is denser, so it sinks beneath the warmer layer, creating a continuous downward movement over an underwater ridge. This movement forms a cascading effect, similar to a waterfall, but on a much larger scale and hidden entirely beneath the ocean's surface. The volume of water involved is immense, with estimates suggesting that it carries around 5 times as much water as all of Earth's rivers combined. Despite its size and power, it remains invisible to the naked eye, detectable only through scientific instruments. It is a reminder that some of the most dramatic forces on the planet operate in complete darkness, shaping the ocean in ways we rarely see. And when you begin to consider the sheer scale of water moving through the ocean, it leads to a broader understanding of just how much water the planet actually holds. The ocean dominates the Earth's water supply, holding about 97% of all the water on the planet. From a distance, it might seem as though water is abundant and easily available, but most of it is not directly usable for human consumption. Seawater contains high levels of dissolved salts and minerals, making it unsafe to drink without treatment. In fact, less than 0.1% of Earth's water exists in a form that is readily drinkable, such as fresh water found in rivers, lakes, and accessible groundwater. The rest is either locked in the oceans, frozen in ice caps and glaciers, or located deep underground where it is difficult to access. This imbalance highlights how limited usable water resources actually are, despite the planet appearing to be covered in water. It also emphasizes the importance of managing fresh water carefully, as it represents only a tiny fraction of the total supply. The ocean, while vast and essential for life, cannot directly meet most human water needs without significant processing. This contrast between abundance and usability shows how the distribution of water shapes life on Earth. And when considering how much of the planet is covered by the ocean, it becomes clear that its depth plays a major role in defining its presence. On average, the ocean has a depth of about 3,688 meters, a figure that reflects the immense volume of water covering the Earth. This average includes a wide range of depths, from shallow coastal areas to deep trenches that plunge far below this number. What makes this depth significant is not just the distance from the surface, but the conditions it creates. As depth increases, pressure rises, temperatures drop, and sunlight disappears, forming distinct layers within the ocean. Most of the ocean exists in these deeper regions, far beyond the reach of human observation. The average depth also means that the ocean holds an enormous amount of water, contributing to its role in regulating climate storing heat, and supporting life on a global scale. It influences weather patterns, ocean currents, and even the distribution of nutrients that sustain marine ecosystems. Despite its importance, much of this deep environment remains unexplored, with vast areas still unknown. The number itself may seem like just a measurement, but it represents a world that is largely hidden from view, filled with conditions and life forms that continue to challenge our understanding of the planet. Beneath the surface of the ocean, there is a vast system of movement that operates on a global scale, slowly connecting all of the world's oceans into a single circulating network. This system is known as the Global Ocean Conveyor Belt, or thermohaline circulation, and it is driven by differences in temperature and salinity. Warm, less dense water moves along the surface, while colder, denser water sinks and travels through the deep ocean. Over time, this creates a continuous loop that carries water across entire ocean basins. What makes this system remarkable is its timescale. A single cycle can take roughly 1,000 years to complete, meaning that water moving through this circulation today may not return to its starting point for many centuries. As it travels, it transports heat, nutrients, and dissolved gases around the planet, playing a crucial role in regulating climate and supporting marine life. It connects distant regions in ways that are not immediately visible, linking polar waters with tropical seas in a slow but powerful flow. This hidden circulation is one of the key systems that keeps the Earth's environment stable. And because it operates so slowly, even small disruptions can have long-lasting effects on the planet. One of the most important parts of this global system lies in the Atlantic Ocean, where cold, dense water sinks and helps drive the entire circulation process. If this Atlantic conveyor were to weaken or collapse, the effects would be significant, especially for regions that depend on the heat it carries. Northern Europe, for example, benefits from relatively mild temperatures compared to other areas at similar latitudes, largely because of the warm water transported by this system. Without it, temperatures in this region could drop by as much as 8 degrees Celsius within a few decades. Such a change would alter weather patterns, shorten growing seasons, and affect ecosystems across a wide area. While a complete collapse is considered unlikely in the near term, scientists continue to monitor changes in ocean circulation closely, as shifts in temperature and salinity could influence its strength. This highlights how interconnected the ocean and climate truly are, with changes in one part of the system capable of affecting distant regions. And as these large-scale processes continue to operate, the ocean is also playing another critical role in balancing the planet's atmosphere. The ocean acts as a major absorber of carbon dioxide, taking in about 25% of the CO2 produced by human activities. When carbon dioxide dissolves in seawater, it forms carbonic acid, which gradually lowers the pH of the ocean. This process is known as ocean acidification, and it has been increasing steadily as more CO2 enters the atmosphere. While the ocean's ability to absorb carbon helps slow the rate of climate change, it also comes with consequences for marine life. Many organisms, especially those that build shells or skeletons from calcium carbonate, are sensitive to changes in acidity. As the water becomes more acidic, it becomes harder for these organisms to form and maintain their structures. This can affect entire ecosystems, particularly coral reefs and other habitats that rely on these species. The ocean's role as a carbon sink is therefore both beneficial and complex, helping to stabilize the atmosphere while also undergoing chemical changes. It is another example of how the ocean is deeply connected to global systems, responding to and influencing changes on a planetary scale. As carbon dioxide continues to dissolve into the ocean, its effects are becoming visible in some of the smallest and most important creatures in marine ecosystems. Among these are pteropods, often called sea butterflies, tiny free-swimming organisms that drift through the upper layers of the ocean. Despite their delicate appearance, they play a crucial role in the food chain, serving as a primary food source for fish, birds, and even large mammals like whales. Their shells are made of calcium carbonate, a material that becomes more difficult to maintain as ocean acidity increases. As the water absorbs more carbon dioxide, it forms carbonic acid, which gradually lowers the pH and reduces the availability of the minerals needed to build these shells. In more acidic conditions, the shells of pteropods can begin to thin, weaken, and even dissolve entirely. This makes them more vulnerable to predators and environmental stress, threatening their survival. Because they sit near the base of many marine food webs, any decline in their population can ripple upward, affecting larger species that depend on them. It is a clear example of how changes in ocean chemistry can impact life at every level, starting with the smallest organisms. And while some areas of the ocean are changing gradually, others have already become so altered that life struggles to exist at all. In certain regions of the ocean, oxygen levels have dropped so low that they can no longer support most forms of marine life. These areas are known as dead zones, and they are often the result of human activity. When large amounts of nutrients from agricultural runoff enter the ocean, they can trigger massive growth of algae. At first, this might seem like an increase in life, but when the algae die, they sink and are broken down by bacteria. This decomposition process consumes large amounts of oxygen from the surrounding water, leaving little behind for other organisms. As oxygen levels fall, fish and other mobile species may try to escape, but those that cannot move quickly enough are left in an environment where survival becomes nearly impossible. Over time, these zones can expand, creating large areas where biodiversity is drastically reduced. Dead zones are now found in many parts of the world, particularly near coastal regions where runoff is most concentrated. They represent a significant disruption to natural ocean systems, showing how changes on land can directly affect life beneath the water. And while some parts of the ocean suffer from too little oxygen, others exist in a delicate balance between different types of water. The Baltic Sea is one of the most unusual bodies of water on Earth, defined by its unique balance between freshwater and seawater. It is the largest brackish water body in the world, meaning its salinity falls somewhere between that of a typical ocean and a freshwater system. This creates a challenging environment for many forms of life. Freshwater species often cannot tolerate the higher salt levels, while marine species may struggle with the reduced salinity. As a result, only certain organisms that can adapt to these intermediate conditions are able to thrive. This limited range of suitable species makes the ecosystem particularly sensitive to changes in temperature, pollution, and oxygen levels. The Baltic Sea is also relatively enclosed, with limited exchange of water with the open ocean, which can lead to slower renewal of its waters. This contributes to issues such as low oxygen levels in deeper areas, further affecting marine life. Despite these challenges, it remains an important habitat for a variety of species that have adapted specifically to its conditions. It stands as an example of how even slight differences in water chemistry can shape entire ecosystems, determining what life can exist and how it survives. Beneath the ocean surface, in places where solid rock meets the sea, there are hidden sources of fresh water that emerge from below the sea floor. These are known as submarine springs, and in some regions they form what are called blue holes. These features are often found in areas made of limestone, where underground aquifers store large amounts of fresh water. Over time, this water finds pathways through cracks and channels in the rock, eventually flowing upward and mixing with the surrounding seawater. When viewed from above, blue holes appear as deep, dark openings in the seafloor, sometimes surrounded by lighter-colored sediment. Inside, the water can be noticeably different in temperature and clarity, as colder fresh water rises from below. In some cases, divers have explored these systems and found extensive cave networks extending far beneath the ocean floor. These environments can support unique ecosystems, with organisms adapted to the unusual mix of fresh and salt water. The presence of fresh water beneath the sea highlights how connected different parts of the Earth's water system truly are, linking underground reserves with the open ocean. It is another example of how the ocean contains features that challenge our expectations, revealing processes that are not immediately visible from the surface. Floating on the surface of the ocean, icebergs may appear as simple masses of frozen water, but they contain a record of the Earth's past hidden within them. As snow accumulates over thousands of years in polar regions, it gradually compresses into ice, trapping tiny bubbles of air along the way. These bubbles preserve samples of the atmosphere from the time the snow originally fell, effectively creating a frozen archive of Earth's climate history. When pieces of this ice break away and form icebergs, they carry these ancient air pockets with them into the ocean. Scientists can study ice cores taken from glaciers and ice sheets to analyze the composition of these trapped gases, revealing information about temperature, carbon dioxide levels, and other atmospheric conditions from hundreds of thousands of years ago. This allows researchers to understand how the climate has changed over long periods of time and to compare past conditions with those of today. Icebergs drifting through the ocean are therefore more than just floating ice. They are fragments of history, preserving details about the planet's environment long before humans began recording it. And while these frozen records move slowly across the surface, the deeper parts of the ocean are defined by a very different condition altogether. As sunlight reaches the ocean's surface, it begins to fade rapidly as it travels downward through the water. Only about 2% of that light remains by the time it reaches a depth of 200 meters. This region marks the lower boundary of the sunlit zone, where photosynthesis can still occur but becomes increasingly limited. Below this depth, the ocean enters a darker environment, where light is no longer strong enough to support most plant life. As you descend further, the darkness becomes complete. By the time you reach depths of around 1,000 meters, no sunlight penetrates at all. This zone exists in permanent darkness, where organisms must rely on other means of survival, such as bioluminescence or chemical energy. The absence of light changes how life functions, influencing everything from feeding behavior to communication. It also affects temperature and pressure, creating conditions that are very different from those near the surface. The rapid loss of light with depth highlights how the ocean is divided into distinct layers, each with its own characteristics. It is a reminder that even though the ocean appears uniform from above, it contains environments that vary dramatically as you move deeper into its depths. In the deep ocean, where sunlight never reaches, light still exists, but it is produced by living organisms themselves. This phenomenon is known as bioluminescence, often described as living light. It occurs when certain organisms generate light through chemical reactions within their bodies, creating flashes, glows, or patterns in the darkness. In an environment where visibility is limited, this light becomes one of the primary ways animals interact with each other. It can be used to attract prey, warn predators, signal potential mates, or even confuse attackers by creating sudden bursts of light. Because so many organisms rely on it, bioluminescence may be one of the most widespread forms of communication on Earth. Entire regions of the deep ocean are filled with faint glows and flickers, forming a hidden network of signals that move constantly through the water. Unlike communication on land, which often depends on sound or sight, the deep ocean relies heavily on light produced from within. This creates a world where darkness is not empty, but filled with activity that is simply invisible to us without the right tools. It is a reminder that even in the absence of sunlight, life finds ways to create its own sources of interaction and connection. And when scientists began to study this phenomenon more closely, they discovered just how common it truly is. Research into deep-sea ecosystems has revealed that bioluminescence is not a rare or isolated trait, but something shared by a large majority of organisms living in these environments. It is estimated that over 76% of deep-sea animals are capable of producing light in some form. This includes a wide range of species, from small plankton and jellyfish to larger fish and squid. Each organism uses light differently, depending on its needs and environment. Some produce steady glows that help them blend in with faint light from above, a strategy known as counter-illumination. Others create sudden flashes to startle predators or signal distress. There are also species that use patterned light displays to communicate with others of their kind, especially during mating. The widespread presence of bioluminescence highlights how important it is for survival in the deep ocean, where other forms of communication are limited. It is not just an unusual feature, but a fundamental part of how life operates in darkness. The deep sea, often imagined as empty and silent, is actually filled with constant visual activity, shaped by countless organisms producing light in different ways. And while this light plays a role in communication and survival, the ocean is also involved in processes that affect the entire planet on a much larger scale. Beyond supporting life in the deep sea, the ocean also plays a crucial role in regulating the Earth's carbon cycle through a process known as the biological pump. This system begins at the surface, where plankton absorb carbon dioxide from the atmosphere during photosynthesis. These microscopic organisms convert carbon into organic material, forming the base of the marine food web. When they die or are consumed, some of this carbon sinks deeper into the ocean in the form of particles, waste, or the remains of organisms. As this material descends, it carries carbon away from the surface and into the deep ocean, where it can remain stored for centuries or even longer. This process helps reduce the amount of carbon dioxide in the atmosphere, playing a key role in regulating the planet's climate. Without it, carbon levels would rise more rapidly, intensifying the effects of global warming. The biological pump is a slow but powerful system, operating continuously across the world's oceans. It demonstrates how even the smallest organisms can influence global processes, linking life at the surface with the deep ocean in a cycle that affects the entire Earth. Far above the deep ocean floor, a slow and continuous process is taking place, one that provides a steady source of food to a world that rarely sees fresh nutrients. This process is known as marine snow, a constant drift of organic material falling from the upper layers of the ocean down into the depths. It is made up of tiny particles, including dead plankton, fragments of organisms, waste, and other microscopic debris. As this material sinks, it forms a gentle, snow-like shower that moves through the water column, eventually reaching the seafloor. For many deep-sea creatures, this is the primary source of energy, as food is scarce in an environment far removed from sunlight. Organisms have adapted to capture and consume this falling material, relying on it for survival over long periods of time. The rate at which marine snow falls can vary depending on conditions at the surface, but it is always present, creating a continuous link between the surface ecosystem and the deep ocean. It is a quiet but essential process, sustaining life in places where direct energy sources do not exist. And as this material settles, it contributes to another process that unfolds at an even slower pace. Once marine snow reaches the seafloor, it becomes part of the sediment that gradually accumulates over time. This buildup happens at an incredibly slow rate, often measuring only about 1 to 10 centimeters every 1,000 years. Unlike the rapid changes we see on land, the deep ocean floor records history in layers that form almost imperceptibly. Each layer contains traces of past life, chemical changes, and environmental conditions, creating a long-term archive of the ocean's history. Over millions of years, these thin layers can build up into significant deposits, preserving information that scientists can study to understand how the Earth has changed over time. The slow accumulation also means that disturbances to the seafloor can take extremely long periods to recover, as new material replaces what has been disrupted only gradually. This delicate balance highlights how different the deep ocean is compared to more dynamic environments. It is a place where time moves slowly, and changes occur over scales that are difficult to observe directly. And while this quiet layering continues far below, the ocean is also home to a system that operates at the speed of modern technology. Running across the ocean floor is a vast and largely invisible network that connects continents in ways most people never think about. These are submarine communication cables, forming a global system that carries over 95% of all international data traffic. Despite the presence of satellites, most of the world's internet, phone calls, and financial transactions depend on these cables, which stretch across thousands of kilometers beneath the sea. They are carefully laid along the seafloor, often following stable routes that avoid areas of high geological activity. Protected by layers of insulation and reinforced materials, these cables are designed to withstand the harsh conditions of the deep ocean, including pressure, currents, and potential damage from natural events. Signals travel through them at incredibly high speeds, allowing information to move almost instantly between distant parts of the world. This system acts as a kind of parallel infrastructure beneath the ocean, supporting global communication without being visible to those who rely on it every day. It is a reminder that the ocean is not just a natural environment, but also a space that humans have integrated into their technological systems, linking the depths of the sea with the flow of information across the planet. In the 19th century, as humans began attempting to connect continents through technology, one of the most ambitious projects was the first transatlantic telegraph cable laid across the ocean in 1858. This cable was designed to carry messages between North America and Europe, reducing communication time from weeks to just minutes. It was a groundbreaking achievement, but the technology behind it was still new and not fully understood. After initial success, operators began trying to improve transmission speed by increasing the voltage sent through the cable. At the time, it seemed like a logical solution, but the cable was not built to handle such high levels of electrical stress. As the voltage increased, the insulation began to fail, and the internal components overheated. Eventually, the cable was damaged beyond repair, effectively melting from within and bringing communication to a sudden halt. The failure highlighted the challenges of working in such an extreme environment, where repairs were nearly impossible and small mistakes could lead to complete system loss. It also marked an important lesson in engineering, showing that pushing systems beyond their limits can have irreversible consequences. Despite this setback, the idea of connecting the world through underwater cables continued, eventually leading to the vast network that exists today. And while human activity has left its mark on the ocean floor, the ocean itself has also recorded events of immense natural power. In 2004, a massive earthquake struck beneath the Indian Ocean, releasing an enormous amount of energy and triggering one of the most devastating tsunamis in recorded history. The force of this event was so great that it did not just affect the immediate region, but the entire planet. When the earthquake occurred, it caused the Earth itself to vibrate, producing a phenomenon often described as the planet ringing like a bell. These vibrations, known as seismic waves, traveled through the Earth and were detected by instruments around the world. What makes this event particularly remarkable is how long these vibrations persisted. Instead of fading quickly, the Earth continued to oscillate for weeks after the initial quake. The energy released was distributed throughout the planet, causing subtle but measurable movements that lasted far longer than the earthquake itself. Scientists were able to study these signals to gain a better understanding of the Earth's internal structure and how energy moves through it. It demonstrated how interconnected the planet is, with a single event in one region capable of producing effects on a global scale. The ocean, in this case, was both the source and the medium through which this immense energy was released and transmitted. And long before such events were measured with modern instruments, the ocean was home to creatures that were equally immense in their own way. Millions of years ago, the oceans were inhabited by one of the largest and most powerful predators to ever exist, a giant shark known as Megalodon. This prehistoric creature dominated the seas, growing to lengths that may have reached up to 18 meters, making it far larger than any modern shark. One of the most striking features of Megalodon was its teeth, which could grow to the size of a human hand. These massive, serrated teeth were designed for cutting through flesh and bone, allowing it to hunt large marine animals, including whales. Fossil evidence of these teeth has been found in many parts of the world, providing insight into the size and distribution of this ancient predator. Unlike bones, which are rarely preserved in sharks due to their cartilaginous skeletons, teeth fossilize well, giving scientists valuable clues about how Megalodon lived and hunted. Its size and strength would have made it an apex predator, capable of dominating its environment with few natural threats. Although it eventually became extinct, its legacy remains one of the most fascinating examples of how large and powerful ocean life once was. It stands as a reminder that the oceans have always been home to creatures that push the limits of what we imagine possible. In the deepest parts of the ocean, near hydrothermal vents on the seafloor, there are environments filled with chemicals that would be deadly to most forms of life. One of the most prominent of these is hydrogen sulfide, a toxic gas that can disrupt biological processes and quickly become lethal in high concentrations. Yet, despite these conditions, entire communities of organisms have evolved to survive and thrive in this environment. These creatures do not rely on oxygen in the same way most life does. Instead, they depend on chemosynthesis, a process where microorganisms use chemicals like hydrogen sulfide to produce energy. These microbes form the foundation of a unique ecosystem, supporting larger organisms such as tube worms, clams, and specialized crustaceans. Many of these animals have developed symbiotic relationships with the bacteria, allowing them to access energy in a place where sunlight does not exist. The water around these vents can be extremely hot, chemically rich, and unstable, yet life persists through highly specialized adaptations. It is an environment that demonstrates how flexible life can be when faced with extreme conditions. What would be toxic and uninhabitable to most organisms becomes a stable and productive ecosystem for others. And in the same ocean where life adapts to toxic chemicals and intense heat, there are organisms that can survive conditions even beyond what is found on Earth. Among the most resilient organisms known to science are tardigrades, often called water bears. These microscopic creatures are found in a wide range of environments, including ocean sediments near hydrothermal vents, where temperatures can approach extreme levels. What makes tardigrades remarkable is their ability to survive conditions that would destroy almost any other form of life. They can endure intense heat, freezing temperatures, high radiation, and even the vacuum of space. When conditions become too harsh, they enter a state known as cryptobiosis, effectively shutting down their metabolism and losing almost all of their water content. In this state, they can remain dormant for long periods, reactivating when conditions become favorable again. In marine environments, particularly near extreme conditions like vents, they demonstrate an ability to tolerate chemical and thermal stress that would be lethal to most organisms. Their presence in such places highlights how life can persist in environments that seem completely inhospitable. Tardigrades are not dominant or large creatures, but their resilience places them among the most extraordinary forms of life on the planet. And while some organisms adapt to survive extreme natural conditions, the ocean is also facing changes driven by human activity. Despite its vastness, the ocean is no longer untouched by human influence. Plastic pollution has spread to nearly every part of the marine environment, from surface waters to the deepest trenches. Even in the Mariana Trench, the deepest known point in the ocean, the traces of plastic have been found, carried there by currents and sinking debris. In polar regions, plastic particles have also been discovered trapped within Arctic sea ice, showing how widespread the problem has become. Over time, larger pieces of plastic break down into smaller fragments known as microplastics, which can be ingested by marine organisms at all levels of the food chain. These particles can carry harmful chemicals and disrupt biological processes, affecting both small organisms and larger animals that depend on them. The presence of plastic in such remote and extreme environments highlights how interconnected the ocean is, allowing pollutants to travel across vast distances. It also underscores the long-lasting impact of human activity, as plastic can persist in the environment for decades or even centuries. Even in the most isolated parts of the ocean, the effects of this pollution are now visible, showing that no part of the marine world remains completely untouched. Even in the most remote and extreme parts of the ocean, human influence has begun to leave a measurable impact. In the depths of the Mariana Trench, thousands of meters below the surface, scientists have discovered microplastics embedded in the tissues of deep-sea fish. These particles are incredibly small, often invisible to the naked eye, and originate from the breakdown of larger plastic debris over time. Carried by ocean currents and gradually sinking, they eventually reach the deepest parts of the ocean, where they become part of the environment. Deep-sea fish, feeding on organic material or smaller organisms, can ingest these particles without any ability to distinguish them from food. Once inside their bodies, microplastics may accumulate, potentially affecting their health and biological functions. The presence of plastic at such depths highlights how far-reaching pollution has become, extending even to places that were once thought to be untouched by human activity. It also raises concerns about how these particles move through the food chain, as organisms at different levels consume one another. The discovery of microplastics in these environments is a clear indication that the ocean is deeply interconnected, allowing materials to travel across vast distances and depths. And while some of this pollution settles in the deepest trenches, much of it remains circulating in the upper layers of the ocean. One of the most well-known examples of plastic accumulation in the ocean is the Great Pacific Garbage Patch, located in the North Pacific Ocean. Despite its name, it is not a solid island of trash that you can see from a distance. Instead, it is a vast area where ocean currents concentrate floating debris, creating a diffuse collection of plastic spread over millions of square kilometers. Much of this material has broken down into microplastics, forming what is often described as a plastic soup. These particles are mixed throughout the water, making them difficult to remove and nearly impossible to see in large quantities at once. The patch is held together by circulating currents known as gyres, which trap debris and prevent it from dispersing easily. Over time, more plastic enters the ocean and becomes part of this system, adding to the concentration. Marine organisms can interact with this material in various ways, sometimes ingesting it or becoming entangled in larger pieces. The scale of the garbage patch reflects the cumulative effect of human waste entering the ocean over decades, demonstrating how long-lasting and widespread this issue has become. And while this floating layer of debris continues to circulate, there are natural movements in the ocean that are just as vast, but far more organized. Within the twilight zone of the ocean, there is a daily movement that involves enormous numbers of organisms, creating what is considered the largest migration on Earth. Many species of fish and other marine animals participate in this vertical journey, moving between deep and shallow waters every single day. During daylight hours, they remain in deeper, darker layers of the ocean, where they are less visible to predators. As night falls, they begin to rise toward the surface, taking advantage of the cover of darkness to feed on plankton and other food sources. This movement can span hundreds of meters and involves vast populations, making it a significant transfer of energy within the ocean ecosystem. By feeding near the surface and returning to the depths, these organisms help transport nutrients and carbon through different layers of the ocean. This process plays an important role in the biological pump, linking surface productivity with deep-sea environments. Despite its scale, this migration remains largely hidden from view, taking place in darkness and often unnoticed by those above the surface. It is a powerful example of how life in the ocean operates on rhythms and scales that are difficult to observe directly, yet essential to the functioning of the entire system. In the vast expanse of the ocean, there exists a creature so large that it surpasses every animal that has ever lived on Earth, including the largest dinosaurs. The blue whale holds this record, reaching lengths of up to 30 meters and weighing as much as 200 tons. Its size is difficult to fully comprehend, as even its tongue alone can weigh as much as an elephant. Unlike the giant predators of the past, the blue whale feeds primarily on tiny shrimp-like organisms known as krill. It does this by taking in enormous mouthfuls of water and filtering out these small creatures using specialized structures called baleen plates. Despite feeding on such small prey, it consumes vast quantities, sometimes several tons of krill in a single day. Its immense size allows it to travel long distances across the ocean, migrating between feeding and breeding grounds. The blue whale represents the upper limit of biological size, showing how life in the ocean can grow far beyond what is possible on land, where gravity imposes stricter limits. Its existence highlights the unique conditions of the marine environment, where buoyancy supports massive bodies that would be unsustainable elsewhere. And within this enormous animal, even its internal processes reflect a scale that is just as extraordinary. One of the most remarkable aspects of the blue whale is not just its size, but the slow and powerful rhythm of its heartbeat. At rest, its heart beats only about 8 times per minute, a pace that reflects the efficiency required to support such a massive body. Each beat pushes large volumes of blood through its circulatory system, supplying oxygen to tissues spread across its enormous frame. What makes this even more unusual is that the sound of its heartbeat can travel through the water over long distances, potentially being detected from several kilometers away. This is possible because sound moves efficiently through water, carrying low-frequency vibrations across vast areas. For scientists, studying these heartbeats has provided insight into how such a large animal manages its energy and oxygen use, especially during deep dives. The slow rhythm helps conserve energy while maintaining essential functions, allowing the whale to operate efficiently in its environment. It is a biological system scaled up to match the size of the animal itself, where even the simplest processes occur on a much larger level. And while blue whales dominate in size and presence, other whales have developed abilities that allow them to explore the ocean in a very different way. Deep beneath the surface, in regions where pressure increases and light disappears, Sperm whales demonstrate an extraordinary ability to dive to extreme depths. These whales can descend to around 3 kilometers below the surface, entering environments that are completely dark and highly pressurized. During these dives, they can hold their breath for up to 90 minutes, relying on stored oxygen and specialized adaptations in their bodies. Their muscles contain high concentrations of myoglobin, a protein that stores oxygen, while their blood can carry more oxygen than that of most other animals. As they dive, their heart rate slows, and blood flow is directed toward essential organs, conserving oxygen for as long as possible. These adaptations allow them to hunt for prey such as squid in the deep ocean, where few other large predators can reach. The ability to travel between the surface and such depths highlights the range of environments that marine mammals can navigate. It is a balance between the need for air and the drive to explore and feed in the depths below. Deep within the massive head of a sperm whale lies one of the most unusual biological structures found in any animal. This space is filled with a substance known as spermaceti oil, which can amount to as much as 2,000 liters in a single whale. For centuries, this material attracted human attention because of its use in products like candles and lubricants, but its true purpose inside the whale remains only partially understood. Scientists believe it may play a role in buoyancy control, helping the whale adjust its position in the water as it dives to extreme depths. By changing the temperature or pressure of the oil, the whale might be able to alter its density, making it easier to descend or ascend. Another theory suggests that the spermaceti organ is involved in echolocation, focusing and directing powerful sound waves that the whale uses to navigate and hunt in complete darkness. These clicks are among the loudest biological sounds on Earth, capable of traveling long distances through the ocean. The exact combination of functions is still being studied, and it is possible that the organ serves multiple purposes at once. This uncertainty highlights how even well-known animals can possess features that are not fully explained. And while sperm whales rely on internal adaptations for survival, other marine mammals have evolved external features that are just as extraordinary. In the cold waters of the Arctic, narwhals are known for the long, spiraled tusk that extends from their heads, often reaching several meters in length. For a long time, this tusk was thought to be primarily a tool for fighting or display, but research has revealed that it serves a much more complex function. The tusk is actually a modified tooth, filled with millions of nerve endings that connect it directly to the whale's nervous system. This makes it an advanced sensory organ, capable of detecting subtle changes in the surrounding environment. Through the tusk, narwhals can sense variations in temperature, pressure, and salinity, helping them navigate and locate prey in icy waters. The outer surface of the tusk contains tiny openings that allow water to interact with these nerve endings, effectively turning it into a highly sensitive instrument. This ability provides the whale with information that would otherwise be difficult to obtain in such a challenging environment. It transforms what appears to be a simple physical feature into a complex biological tool. The narwhal's tusk is a clear example of how evolution can adapt a basic structure into something highly specialized. And while some marine animals develop advanced sensory systems, others rely on behavior to maintain connection and safety within their environment. Along the ocean's surface, in calmer coastal waters, sea otters display a behavior that reflects both their social nature and the challenges of their environment. When resting or sleeping, they often hold on to each other's hands, forming groups known as rafts. This simple action helps prevent them from drifting apart due to currents or waves. Unlike many marine animals, sea otters do not have thick layers of blubber to keep them warm, so they rely on their dense fur and constant grooming to maintain insulation. Staying close together also helps conserve heat and provides a sense of security within the group. In some cases, they may wrap themselves in strands of seaweed or kelp, anchoring their bodies in place while they rest. This behavior reduces the risk of being carried away while asleep, allowing them to remain in a familiar and safe area. The act of holding hands may appear almost human, but it serves a clear and practical purpose in the ocean environment. It is a reminder that survival is not always about physical strength or extreme adaptations, but sometimes about simple behaviors that help maintain stability and connection in a constantly moving world. In the structured communities of coral reefs, clownfish display a reproductive system that is both unusual and highly efficient. All clownfish are born male, living in small groups organized around a strict hierarchy. At the top of this group is a single dominant female, followed by a breeding male, and then several smaller non-breeding males. If the dominant female dies or is removed, the system quickly adjusts. The largest male in the group undergoes a biological transformation, changing sex to become the new female. This process involves hormonal and physical changes that allow the fish to take on the reproductive role previously held by the dominant individual. The next largest male then moves up in rank to become the breeding male. This ability ensures that reproduction can continue without the need to find new mates, which can be difficult in the complex and competitive environment of a coral reef. It is a system that maintains stability within the group while allowing flexibility when conditions change. The relationship between clownfish and their host anemones further supports this structure, providing protection and a defined territory. This adaptation highlights how social organization and biology can work together to ensure survival. And while clownfish rely on transformation within a group, other marine animals survive by transforming how they appear to the outside world. In the shallow waters of the Indo-Pacific, the mimic octopus has developed one of the most advanced forms of camouflage and imitation known in the animal kingdom. Unlike typical camouflage, which involves blending into the environment, this octopus actively changes its shape, color, and behavior to resemble other marine animals. It can imitate more than 15 different species, including lionfish, flatfish, and sea snakes, each chosen depending on the situation and the type of predator it encounters. By spreading its arms and altering its movement, it can mimic the appearance of a venomous or unpalatable species, discouraging potential attackers. This ability requires not only physical flexibility, but also a form of decision-making, as the octopus must select the most effective disguise for the threat it faces. Its skin contains specialized cells that allow rapid changes in color and pattern, while its soft body can be reshaped into a wide range of forms. This combination of traits allows it to shift from one identity to another within moments. It is not simply hiding, but actively deceiving other animals, using illusion as a primary defense. This level of adaptability shows how intelligence and physical design can combine to create highly effective survival strategies. And while the mimic octopus relies on changing its outward appearance, other marine creatures operate with internal systems that are equally unconventional. Starfish, also known as sea stars, are another example of how different marine life can be from what we expect. They do not have a centralized brain like most animals, nor do they possess blood in the traditional sense. Instead, they use seawater to circulate nutrients and oxygen throughout their bodies, moving it through a system of canals known as the water vascular system. This system also powers their movement, allowing them to extend and retract hundreds of tiny tube feet that help them walk, grip surfaces, and capture prey. Their nervous system is not concentrated in one location, but distributed across their arms, with a central nerve ring coordinating activity. This means that each arm can respond to stimuli independently to some degree, allowing the starfish to react to its environment without relying on a single control center. Even if one arm is damaged or lost, many species can regenerate it over time, restoring lost function. This decentralized design makes them highly resilient and adaptable. It is a form of life that operates without the structures we typically associate with complex organisms, yet it functions effectively in its environment. Hidden within coral reefs are organisms that exist on timescales far beyond what we usually associate with marine life. Some species of coral can live for thousands of years, slowly building their structures layer by layer over centuries. Among the most remarkable are black corals, which have been dated to over 4,000 years old. These corals grow at an extremely slow rate, adding only small amounts to their skeletons each year. Over time, this gradual growth creates intricate, tree-like formations that can persist for millennia. Because of their longevity, black corals act as natural records of environmental conditions, preserving information about ocean chemistry and climate over long periods. Scientists can study their structure to gain insight into how the ocean has changed across centuries. Despite their age, these corals are fragile and vulnerable to disturbance, as damage can take hundreds or even thousands of years to repair. Their existence highlights how some parts of the ocean operate on timescales that are almost impossible to fully grasp. While human history spans only a few thousand years, these organisms have been growing quietly through much of that time. And beyond their age, corals also possess abilities that allow them to interact with their surroundings in ways that are not immediately visible. Within a coral reef, communication does not happen through sound or movement alone. Corals are capable of sending chemical signals through the water, allowing them to respond collectively to changes in their environment. When a coral becomes stressed, whether from rising temperatures, pollution, or physical damage, it can release specific compounds into the surrounding water. These chemicals are detected by nearby corals, triggering defensive or adaptive responses even before they are directly affected. This form of communication helps coordinate the behavior of the reef, allowing it to respond more effectively to threats. For example, some corals may increase their production of protective substances or adjust their internal processes to cope with stress. This chemical signaling creates a network of interaction that connects individual organisms into a larger system. It is not communication in the way animals exchange signals, but it serves a similar purpose, allowing information to spread across the reef. This ability helps maintain stability in an environment that can change rapidly, especially under external pressures. It reveals that coral reefs are not just collections of individual organisms, but interconnected communities capable of responding together. And while corals rely on subtle chemical signals, other marine creatures use direct physical force in ways that are far more immediate and intense. Among the many powerful creatures in the ocean, the mantis shrimp stands out for its ability to deliver one of the fastest and most forceful strikes in the animal kingdom. Using its specialized front limbs, it can punch with such speed that the impact is capable of shattering aquarium glass. The motion is so rapid that it creates a phenomenon known as cavitation, where a bubble forms and collapses almost instantly, generating additional force and heat. This means the strike is not just a physical impact, but also accompanied by a secondary shock wave. The combined effect allows the mantis shrimp to break through the hard shells of prey such as crabs and mollusks with ease. Despite its relatively small size, it has developed a mechanism that rivals some of the most powerful forces found in nature. The energy released in each strike is concentrated into a very small area, making it extremely effective for both hunting and defense. This ability demonstrates how evolution can produce highly specialized tools, allowing even small organisms to dominate their environment. It is a reminder that strength in the ocean is not always about size, but about how efficiently force can be generated and used. In the deep ocean, where food is scarce and opportunities to feed are unpredictable, some fish have evolved the ability to take advantage of whatever they encounter, no matter its size. Certain deep-sea species possess highly expandable stomachs that allow them to swallow prey larger than their own bodies. Their jaws can stretch wide, and their bodies are designed to accommodate sudden increases in volume. This adaptation is essential in an environment where meals may be infrequent, and passing up an opportunity could mean going without food for long periods. Once the prey is consumed, the fish can slowly digest it over time, extracting as much energy as possible. This strategy reduces the need for constant hunting and allows the fish to survive in conditions where resources are limited. The flexibility of their bodies reflects the challenges of life in the deep sea, where survival often depends on being able to adapt to extreme circumstances. It is a clear example of how organisms adjust their physical structure to meet the demands of their environment. And while these fish adapt to scarcity by maximizing each feeding opportunity, the ocean floor itself is shaped by forces that create structures of immense size and power. In regions where the Earth's crust is active beneath the ocean, hydrothermal vents can form towering structures that rise dramatically from the sea floor. One of the most notable examples was a massive black smoker vent that scientists named Godzilla. This structure reached a height of approximately 45 meters, making it one of the tallest hydrothermal formations ever observed. Black smokers form when superheated, mineral-rich water is expelled from beneath the seafloor and meets the cold ocean water, causing minerals to solidify and build up over time. Layer by layer, these deposits create chimney-like structures that can grow for years or even decades. The vent known as Godzilla stood as a striking example of this process, dominating its surroundings until it eventually collapsed in the 1990s. Such collapses are part of the natural cycle of these formations, as the continuous flow of material weakens and reshapes them over time. These vents are not just geological features, but also support unique ecosystems, where organisms rely on chemical energy rather than sunlight. The rise and fall of structures like Godzilla highlight how dynamic and ever-changing the ocean floor can be. And even in the darkness surrounding these vents, the deep ocean is far from silent. Within the ocean's midnight zone, which extends from about 1,000 to 4,000 meters below the surface, there is no sunlight at all. It is a place of complete darkness, where pressure is immense and temperatures are low. Despite these conditions, the environment is not silent. It is filled with a range of biological sounds produced by creatures that are still largely unknown to science. Some of these sounds come from movements, feeding activity, or communication between organisms, while others are generated by processes we do not yet fully understand. Sensitive instruments have recorded clicks, pulses, and low-frequency noises that travel through the water, revealing a hidden layer of activity in the deep sea. These sounds can carry over long distances, taking advantage of the way sound moves efficiently through water. For many organisms, sound may serve as an important means of interaction in a place where visibility is limited. The presence of these signals shows that the deep ocean is not an empty or inactive space, but one filled with life that is constantly interacting in ways we are only beginning to detect. It is a reminder that even in the most remote and dark parts of the ocean, there is ongoing activity that remains largely unexplored. Despite centuries of exploration and scientific study, the ocean remains one of the least understood environments on Earth. A large portion of its depths has never been directly observed, and as a result, scientists believe that there may be more undiscovered species in the ocean than all the known species currently identified on land. This idea is based on the vastness of the marine environment, especially in deep-sea regions where conditions are difficult to access and study. Many organisms that live in these areas are small, hidden, or exist in habitats that are rarely explored, such as deep trenches, underwater caves, and hydrothermal vent systems. Each new expedition often reveals species that have never been seen before, suggesting that the ocean still holds an enormous amount of biological diversity waiting to be documented. The possibility that so much life remains unknown highlights how incomplete our understanding of the planet truly is. It also shows that discovery is not limited to distant worlds or outer space, but continues within the oceans here on Earth. And as scientists continue to explore, they are steadily uncovering new forms of life at a surprising rate. Every year, researchers studying the ocean identify and describe thousands of new species, with estimates suggesting that around 2,000 are discovered annually. These discoveries range from microscopic organisms to larger, more complex animals, each contributing to a broader understanding of marine ecosystems. Advances in technology, such as deep-sea submersibles, remotely operated vehicles, and genetic analysis, have made it possible to explore regions that were once inaccessible. These tools allow scientists to observe organisms in their natural habitats and analyze their characteristics in greater detail. Even so, the rate of discovery indicates that we have only begun to scratch the surface of what exists beneath the waves. Many species are found in extreme environments, such as the deep ocean, where unique conditions have driven the evolution of unusual adaptations. Others are discovered in more familiar areas, showing that even well-studied regions can still hold surprises. The continuous discovery of new species emphasizes how dynamic and complex the ocean is, with ecosystems that are still being mapped and understood. And as organisms are discovered and studied, scientists also observe how life moves and changes within different layers of the ocean. In the ocean's midwater region, known as the mesopelagic zone, there is a process sometimes referred to as the zone of no return. This term describes what happens to many fish and other organisms when they die in these depths. Located between roughly 200 and 1,000 meters below the surface, this zone is where light fades and pressure increases. When a fish dies here, its body often begins to sink deeper into the ocean, moving beyond the reach of surface currents and into darker, more isolated layers. As it descends, it becomes part of the deep ocean's food chain, consumed by scavengers or broken down by microorganisms. Because of this downward movement, the remains rarely return to surface waters, effectively removing nutrients from the upper layers of the ocean. This process plays a role in the biological pump, transferring organic material into the deep sea where it can remain for long periods. The idea of a zone of no return reflects how the ocean is structured in layers, each with its own conditions and processes, and how movement between these layers can be one-directional. Even in the deepest parts of the ocean, where darkness is complete and pressure is immense, the water is never truly still. There is a constant, slow movement shaped by forces that operate on a planetary scale. One of the most important of these is the rotation of the Earth, which influences ocean currents through a phenomenon known as the Coriolis effect. As the planet spins, it causes moving water to curve in predictable patterns, creating large-scale circulation systems that extend from the surface down into the deepest layers. These currents do not move quickly, especially at great depths, but they are persistent and continuous, carrying water, heat, and nutrients across vast distances over long periods of time. Even at the bottom of the ocean, subtle flows exist, connecting distant regions in a slow but steady motion. This means that no part of the ocean is completely isolated or motionless. The idea of stillness is only an illusion created by the vast scale and slow pace of these movements. In reality, the ocean is always in motion, driven by forces that operate far beyond what we can easily observe. And as these movements continue over time, they are also connected to processes that affect the entire planet, including the length of our days. The interaction between the ocean and the Earth's rotation goes beyond shaping currents. It also plays a role in gradually changing the length of a day. Ocean tides, driven by gravitational forces, create friction as water moves across the surface of the Earth. This friction acts as a kind of resistance, slowly reducing the speed of the planet's rotation. As a result, the length of a day increases over time, though the change is extremely small. Scientists estimate that this process adds about 1.4 milliseconds to the length of a day every century. While this increase is too small to notice in daily life, over millions of years it becomes significant. In the distant past, days on Earth were shorter, and the planet rotated more quickly than it does today. The gradual slowing of rotation is a continuous process, influenced largely by the movement of ocean water and the forces acting upon it. It is an example of how the ocean is not just shaped by the Earth, but also contributes to shaping the planet itself. And at the center of these tidal movements are gravitational forces that come from beyond the Earth. The tides we observe in the ocean are primarily driven by the gravitational pull of the Moon, but the Sun also plays an important role in this process. As the Earth rotates, the gravitational forces of both the Moon and the Sun act on the ocean, creating bulges of water that result in rising and falling tides. When the positions of the Earth, Moon, and Sun align, their combined gravitational pull produces what are known as spring tides. During these periods, the difference between high and low tide becomes much more pronounced, leading to stronger and more extreme tidal changes. Conversely, when the Moon and Sun are positioned at right angles relative to the Earth, their gravitational effects partially cancel each other out, resulting in weaker tides known as neap tides. This constant interplay between celestial bodies creates a rhythmic pattern in the ocean, influencing coastal environments and marine life. The tides are therefore not just a local phenomenon, but part of a larger system that connects the Earth to its surroundings in space. The ocean is not just a body of water, but also a vast reservoir of dissolved gases that play a crucial role in regulating the Earth's climate. Within seawater, gases such as oxygen, nitrogen, and carbon dioxide are constantly being absorbed, stored, and exchanged with the atmosphere. This exchange happens at the ocean's surface, where wind, temperature, and biological activity influence how much gas enters or leaves the water. Once dissolved, these gases can remain in the ocean for long periods, especially as currents carry them into deeper layers where they are isolated from the atmosphere. Carbon dioxide is particularly important in this process, as the ocean absorbs a significant portion of what is released into the air. Over time, this helps moderate the rate of climate change, but it also leads to chemical changes within the water itself. Oxygen levels, on the other hand, are essential for marine life and are influenced by both surface exchange and biological processes such as photosynthesis and respiration. Because the ocean circulates slowly, the distribution of these gases can affect climate patterns over centuries or even millennia. It is a system that operates on a global scale, linking the atmosphere and the ocean in a continuous exchange. And within this vast and connected environment, there are locations so remote that they seem almost completely detached from the rest of the world. In the South Pacific Ocean, there is a location known as Point Nemo, often described as the most isolated place on Earth. It is the point in the ocean that is farthest from any land, surrounded by thousands of kilometers of open water in every direction. The nearest land masses are small and distant islands, each separated by vast stretches of ocean. Because of this extreme isolation, the closest humans to Point Nemo are sometimes not on Earth's surface at all, but aboard spacecraft orbiting the planet, such as those on the International Space Station. This comparison highlights just how remote the location truly is. The waters around Point Nemo are relatively low in marine activity compared to other regions, partly due to limited nutrient supply, which makes it less attractive to many forms of life. Its isolation has also made it a unique reference point for scientific and navigational purposes. It represents the most distant part of the ocean from human presence, a place where the influence of land is almost entirely absent. And because of this remoteness, it has taken on an unusual role in modern technology and space exploration. Due to its extreme distance from human populations and shipping routes, Point Nemo has become a designated area for the controlled re-entry of decommissioned spacecraft. When satellites or space stations reach the end of their operational life, they are often guided to re-enter the Earth's atmosphere in a way that ensures any surviving debris falls into this remote part of the ocean. This region is sometimes referred to as a spacecraft graveyard, where fragments of human-made objects return from space and settle in the sea. The choice of this location minimizes the risk to people and infrastructure, as the surrounding area is largely uninhabited and rarely visited. Over time, parts of various spacecraft have descended into these waters, marking the end of their journeys. This practice reflects how even the most advanced technologies eventually return to the Earth, often in places far removed from human activity. It also highlights the connection between the ocean and space, showing how the most remote parts of our planet are used to manage objects that once orbited far above it. If all the ice in Antarctica were to melt, the impact on the planet would be enormous and far-reaching. Antarctica holds the vast majority of the world's freshwater ice, and when converted into liquid water, It would raise global sea levels by roughly 60 meters. This increase would be enough to submerge most coastal cities around the world, including many of the major population centers where millions of people currently live. Entire regions would be permanently flooded, coastlines would be redrawn, and ecosystems would be dramatically altered. Low-lying countries and island nations would be among the first to be affected, but even inland areas would experience changes due to shifting weather patterns and displaced populations. The process of melting at that scale would take a long time, but even partial melting could cause significant disruption. It highlights how closely connected the polar regions are to the rest of the planet, acting as a kind of global water reserve. The stability of this ice is therefore critical, not just for Antarctica itself, but for the entire world. And while large-scale changes like this reshape the planet, individual marine species have developed their own ways of adapting to threats in their environment. In many parts of the ocean, survival depends on protection as much as it does on speed or camouflage. Some fish have evolved natural armor plating, giving them a physical defense against predators. Instead of relying solely on scales, these fish develop hardened outer layers made of bony plates that act like a shield. This armor can cover large portions of their bodies, reducing the chance of injury during attacks. In environments where predators are common, this added protection can make the difference between survival and being eaten. The structure of this armor varies between species, with some forming interlocking plates that allow for movement while still maintaining strength. Others have rigid coverings that prioritize defense over flexibility. While this protection can make them slower or less agile, it provides a level of security that compensates for those limitations. It is an example of how evolution balances trade-offs, shaping organisms based on the pressures they face in their environment. These armored fish show that survival is not always about escaping danger, but sometimes about being able to withstand it. And just as some species develop external defenses, the ocean itself contains structures that form deep and hidden features beneath the surface. Scattered across certain parts of the ocean floor are formations known as blue holes, deep underwater sinkholes that extend far below the surrounding seabed. These features are often formed in limestone regions, where rock gradually dissolves over time, creating large cavities. When sea levels rise or the land shifts, these cavities can become submerged, forming vertical shafts that lead into deeper chambers and cave systems. From above, blue holes appear as dark, circular patches in the water, contrasting sharply with the lighter surrounding areas. Their depth can vary greatly, with some extending hundreds of meters downward. Inside, conditions can change rapidly, with differences in temperature, salinity, and oxygen levels creating distinct layers. Some blue holes contain unique ecosystems, while others may have zones where oxygen is so low that most life cannot survive. They are often difficult to explore due to their depth and complex structure, making them some of the more mysterious features in the ocean. These formations add to the ocean's already diverse landscape, showing that beneath the surface lies a world shaped by both geological and chemical processes over long periods of time.